Welcome to a code report solution video, and in this video we are going to have some fun with APL and do a little bit of point-free or tacit programming, and we're going to do that while solving this week's Perl Weekly challenge, which is similar to LeetCode. They just post a couple problems and then you can solve it in whatever language you want. So let's hop straight into things. The first question is task number 1, Pandigital numbers. It says to write a script that generates the first 5 Pandigital numbers in base 10. And as per the Wikipedia, it says a Pandigital number is an integer that in a given base has among its significant digits each digit used in the base at least once. So if we hop over to the Pandigital number Wikipedia page, you can see here, I'm not going to read through this in detail, but if we look at, so basically wants us to generate the smallest Pandigital number in each base. So we're going to do base 1, 2, 3, 4, and 5. And you can see that it's the smallest one such that all of the digits in that base show up. So for base 3, all of the numbers 0, 1, and 2 show up. And that'll be when converted to base 10, 11. So you can solve this a couple different ways. We're going to do it 2 different ways. It gives you this nice formula here that basically if you just program this and plug in B as your base, you're going to get your number. So let's do that first. So let's zoom this into this formula a tiny bit more so folks can see as we hop back and forth. And we will build this up in APL pretty confusingly in a point-free or tacit style. So we're going to start with the first term, which is b to the b minus b over b minus 1 squared. So, and we'll do this for base 3 at first, and then we'll generate the first 5 or the first 10 or however many. So if we start with our base 3 and we want to get b to the b minus b, b to the b is just the power operator. So we could do 3 like this, but we can do this point-free by using the w combinator in this case, which will basically duplicate 3 as the argument on both the left and right. So this is the same thing. And what we want is b to the b minus b. So we can make use of a 3 train or a fork. So this is now b to the b. Our binary operation is going to be minus. And to get b, we just want to use the I combinator or the identity function, which is called same in APL. So if we do this, we should get 24. So this is going to evaluate to 3 to the power of 3 minus 3. And we are done with the numerator of our first term. So let's focus on the denominator now, which, just to refresh, is going to be b minus 1 squared. So we can first turn this into another 3 train, which if we just want to do something super simple, we can use catenate as our binary operation and then identity. So this is going to give us 24, 3. But what we really want is we want this to be division. And we want this to be b minus 1 squared. So we can get minus 1 pretty quickly, I believe. So if we go minus 1 and compose these two. And so actually, let's just stick with catenate for a sec. So sure enough, we get 24, 2. And then we want this to be squared. So actually, let's do this a different way. Let's do a train. So 1 minus, and then, so this is going to be 1 minus our base, or 3 in this case, but really what we want is 3 minus 1. So in order to do that, we make use of the C combinator, aka flip. So this is going to flip the order. So instead of having 1 minus 3, we're going to end up with 3 minus 1. So this should still give us 24, 2. And now we want to square this. So the way to do that is to once again use the power operator. But this is going to be 2 to the power of 2, or 2 to the power of the evaluation of this, which happens to be the same number. But really, we want this to be once again flipped. So we're going to use the C combinator, which is known as the commute operator in APL. So if we do this, we should get, 4. And then now we can just replace our catenate with division, and now we have our first term. So let's just check that that's right. So 3 to the power of 3 is 27, minus 3 is 24, divided by 3 minus 1 is 2 squared, 24 divided by 4 is 6. So looks like we got it right. We will find out when we actually get finished with this formula, and we do it for not just one base, but the first 5 or 10 bases. So the next term we have is b minus 1 times b to the b minus 2. So once again, we can turn what we currently have into a simple fork. And we do that by doing identity and catenate. So now we have 3, 6. So we want to turn this into the b minus 1 times b to the b minus 2. So let us turn this into a fork where we'll start with, once again, the binary operation being catenate, but we will eventually replace this with multiplies because we're multiplying 2 terms here. So catenate, and we want 1 minus, which we did before. So that's just basically you have a binary operation and you're doing partial application here so that you end up with a unary operation. So that takes care of our minus 1, and then we want b to the power of b minus 2. So I think we can just do another fork here, which is going to be power in the middle, and then minus 2 and identity. So this will be identity, and this will be minus 2. So what should we expect this to be? 3 to the power of 3 minus 2 is just going to be 3, and so we should get 3, 2, 6. Correct. So now we can replace this catenation with multiplication. 3 times 2 is 6, so that looks right. And then the only thing we have to do now is add the negative 1 to the start of our list of numbers. And now we have all of the terms that make up this formula. So we can just simply do a plus reduce, aka a sum, and we should get our value. So in base 3, you can see, sure enough, that 11 is our answer. And so if we simply just, instead of doing this, we do it iota 5, 2, 11, 75, 694. So this doesn't work for base 1 clearly, but it seems to work for all the other ones. So let's see if we change this to 10 as well. That looks to be correct. So let's take a look at what we have here. We can call this pan for short. Get rid of these outer parentheses. And can we simplify anything here? Not really, I don't think so, in terms of just removing the parentheses. So this is a 3 train here, but because of the way this is evaluated, you don't, as long as you just have a 3 train as your right tine, you don't need the parentheses. But a 3 train as your left tine, you do need the parentheses. Otherwise, it won't parse correctly, I believe. So obviously, this is a bit, most people are going to be like, this is completely unreadable. And I agree. This is taking point free or tacit too far. So let's code this same thing, but what I would consider a more readable method. So let's call this pan2. And if we hit Control Enter, we should get a little screen up here. So the alternative way to do this would be to write a little function here where we sort of code these zoom out a tiny bit here so this is easier to see. So our first term was what? It was b to the b minus b. So I think we can still use the W combinator in a 3 train to do this. This was, yeah, b to the b minus b. And omega is going to be our argument, and we can put a little comma here that sort of shows this is b to the b minus b. Oh, except I should not have done that. No. And in hindsight, we shouldn't call this b because we're going to use b as a variable name in a sec. Then we have the term b minus 1. Which is very clear. And then we have the term, what is the other term that we have? B to the b minus 2. So what's the clearest way? Power in the middle, minus 2. Yeah, I still think that's the nicest way to do this. And then you can go b to the b minus 2. And then once you have all of this, you can basically, it's just going to be a divided by b squared. B squared plus b times c. Minus 1. And I think I got that right. Let's just copy this in case. And then do this over iota 10. It does not look like I got it right. So let's see if we can quickly identify my mistake. So should be division. And once again, copy this. And sure enough, there we go. So minus the fact that this doesn't work for 1, it's pretty cool. And I would say that, you know, reluctantly, or not reluctantly, but that this is the more readable version. Although there is something fun about building up a tacit solution, even if ultimately what you would put in production is something more similar to what this is. The other way that you can solve this Pandigital problem, which we will call Pan 3, is by actually sort of converting it to the base and then checking if you have the unique number of elements. So say we have the number 11. So we would basically just like generate the first 1,000 or something elements and then convert this to base 3. So I believe that is done with the power. We do this. And then so we want to check that the size of this is equal to 3. And that actually, so we just want to check that the unique elements are equal to 3. And then if we were to do 10, we should get false. So let us, it would be actually interesting to see if we could turn this into point free. So yeah, so now if we do like iota 20, and then we use where to pull out the values which correspond to 1, and then just pick the first of these. So to recap, this is converting your base 10 number into base alpha, where omega is your base 10 number. And then it's checking, are the unique values, that's what this is here, are the number of those, so the tally is the count of the unique values in that base 3 number, is it equal to the base? And anytime that is the case, you'll get a 1. And if you do that over a certain number of values, and then use where, which is known as indices in J, it will basically give you all of the values that this returns true for. And then we can just use first to pick out the first one. So the way to do this, so let's call this Pan 3. And then what we want is Pan 3 to be used in a function where we are composing the base or binding the base with this function. And then we want to do this over like the first 100. So let's see if we can do this for, and let's avoid the first one. I think I have boxing turned off, so this is making this a bit hard to read. So then if we were to go do our indices here, and our first here. Then change this to just some arbitrary large number, which is very inefficient. There's probably some way to like sort of simulate a while loop, but I do not know how to do that. And sure enough, yeah. So I think we need to make this just big enough in order to get the correct value for the first. So I guess technically change this to 4, keep this at 1,000, append 1. And that is your first 5 Pandigital numbers using an alternative method, which is going to be a lot less efficient, but sort of just fun to work through how to do this. All right, this video is getting too long, so let's very quickly go and solve the task number 2, which actually, because we're using APL, is going to be simpler than the first task. So it's given 2 positive numbers, m and n. Write a script to generate the multiplication table, display the count of the distinct terms. So you can see simply multiplication table given 3 and 5, get the distinct terms, print those out, and then print the count of them. So this is going to be super straightforward in APL because this is sort of dealing with matrices, and we have all the built-ins that we need to do this very quickly. So let us hit enter a couple times and start fresh. So task 2. So say we're doing 3 and 5. What we need to do is first go iota 3, which is going to give us our sequence, iota 5, and then if we use outer product with both of these, and it's a multiplication times table, so this is basically built in what we need to do here, and iota 5. This is going to give us our multiplication table. So we're already done with that step. And note, once again, we can do something neat with tacit programming. I mentioned this in a recent ADSP, the Algorithms and Data Structure podcast that I have, that whenever you have a unary operation that's being applied to 2 different arguments that's the same, and then a binary operation, this is the psi combinator. So you can actually, they call this over, I believe. But if you have your binary operation, then you have over, and then you have iota as your unary operation. You can do this, and you're going to get the same thing, which is pretty awesome. And so now that we have this, we should create a function. So, well, actually, we can just do this without creating a function first. So how do you get the unique items? You ravel this, and then you use unique. And so that'll be your distinct terms. And how do you get the count of these? You just do tally. So pretty beautiful. We've got outer product, we've got ravel, we've got unique, we've got tally, everything we need to solve this problem. So if we copy and paste this, and we just call our function DTC for distinct term count, let us first alpha omega, and we'll call this T for table, and then we actually want to output this, so we do that. This is basically for printing to your screen, and then we want to do the same thing, and we're going to call this distinct, or write distinct, what do they call it, distinct terms. And then do the unique ravel t. And we could save this to a variable, but I don't want to do that. So we're just going to do the computation twice. And then we go count, catenate, same thing, and we throw a tally in front. And if I did this correctly, we should get exactly what we want. So escape this, 3, 5, boom. God, you gotta love APL. So we can do this for the other test case, 3, 3. Yeah, I mean, we could change this to, whatever we want. 5, 4. Pretty cool. Maybe in a different video, I could modify this solution to prefix the table with sort of the header titles and the row titles and the column titles. But I'm going to leave the video here because I'm probably already close to the or above the 20-minute mark, which is getting pretty long for one of these videos. But I hope you enjoyed watching this. I love solving these little small problems in APL, and hopefully you had fun watching. You learned something. I will leave links to all these solutions, sort of the GitHub pages, and also a link to the Perl Weekly Challenge website if you want to check out some of these problems, as well as links to the RIDE editor that I'm using right now and Dialog APL. If you got any questions, feel free to leave them in the comment section down below. If you have alternative solutions, especially if you know how to do that sort of while loop instead of having to hard code the 1000 in there, YouTube hates everything Unicode. I suggested in an earlier video using the try APL hyperlinks. That actually embeds the Unicode in them, so YouTube deletes those as well. So the best solution that I've seen is to basically just create like a GitHub gist or a GitHub file and link that. However, I've heard that YouTube even removes some of those hyperlinks as well. So yeah, it is a battle trying to post alternative solutions. But yeah, if you can find a way, feel free to post it in the comments down below. I always love to look at alternative solutions. And yeah, I'll leave that video here. So hope you enjoyed, hope you learned something, and have a great day.